Today we're going to talk about how to show logical equivalence using true-false assignments. Proving logical equivalence using truth tables is not difficult for simple logical statements, such as P implies Q. But when logic statements become complex or contain more variables, the number of rows required in the truth table, and definitely the potential for making a mistake, quickly renders this impractical. Proving logical equivalence using laws and rules of logic that directly follow from the original statement can prove equivalence of complex statements with many variables. However, this method is not always intuitive or obvious. On the other hand, proving the statements are equivalent by describing possible cases of each logical statement is easier than both of the other methods when some cases can be simplified and combined. For example, consider that we want to show that P implies Q is equivalent to not Q implies not P, the contraposition. The only case that makes these statements false is when P is true and Q is false. It is true for all other cases. In a real-world scenario, for example Wikipedia's action against SOPA, the Stop Online Privacy Act, we can describe the situation with the statement, if Wikipedia blacks out their website, then the public will learn about SOPA. In this case, proposition P is Wikipedia blacks out their website, and Q is the public will learn about SOPA. The contraposition of this statement is not Q implies not P. That is, if the public does not learn about SOPA, then Wikipedia did not black out their website. Before we start our proof, it is important to note that in the terms of our example, it is not possible for Wikipedia to have blacked out their website and for the public to not learn about SOPA at the same time, because then P implies Q would give true implies false, which makes the statement false. As we mentioned earlier, P implies Q is automatically true when P is false, so we will first consider that P is false. In the case of our example, this would mean that Wikipedia did not black out their website. The logical statement P implies Q then becomes false implies Q, which is always true. The value of Q is irrelevant. That's basically saying that if Wikipedia did not black out their website, we don't need to know whether the public learned about SOPA. Now we check the contrapositive to see if it is also true in that case. When P is false, not P is true. So the second logical statement becomes not Q implies true. Since both false implies true and true implies true are true, the value of Q is again irrelevant, and the statement is always true. Again, using our example, that's saying that if the public learned about SOPA, then we can't tell whether or not Wikipedia blacked out their website or not, just from that information. We have now proved that P implies Q and not Q implies not P have the same truth values when P is false, but we also need to show that they have the same truth values when P is true. When P is true, that is, Wikipedia blacked out their website, the first logical statement, P implies Q, becomes true implies Q. Whether true implies Q is true or not depends directly on whether Q is true or false. That is to say, if Q is true, and the public learned about SOPA, then true implies true is true, so our logical statement is true. If Q is false, and the public did not learn about SOPA, then true implies Q is false, so our logical statement is false. Now we've shown the cases for the left side logical statement of the equivalence, so we need to show that the second logical statement, not Q implies not P, is also true when P is true and Q is true, and also false when P is true and Q is false. This is easy to see. In the first case, not Q implies not P becomes false implies false, which is true. That means if the public did not learn about SOPA, then Wikipedia did not raise awareness by blacking out their website. In the second case, not Q implies not P becomes true implies false, which is false. That statement says that if the public did not learn about SOPA, then Wikipedia must have blacked out their website. Stated in English, we see that in our real-world example it is obviously false in that case as well. In our example, it is not possible for Wikipedia to have blacked out and the public not to know about SOPA simultaneously. So the truth values of the logical statements agree with our real-world example's logic. So we see that for the same combinations of P and Q, the two statements P implies Q and not Q implies not P have identical truth values. What we just did is very similar in a lot of ways to a truth table. However, we defined cases and applied them to the statement instead of drawing a table. The key difference is that we were able to group all of the cases when P is false, whereas in a truth table we would still have to list out both rows. The only cases we considered were P is false and Q is false, P is true and Q is false, and P is true and Q is true, which is 3 cases, whereas a truth table would have had 4 rows. This may not seem like much of a difference, but if we were working on a more complex statement with more variables, it's likely that most of the cases could be grouped together in much the same way we did here, keeping our proof short and simple. Consider a statement with 4 variables like P implies the expression not Q implies the expression not R implies S. A truth table for this statement would have 16 rows and probably several columns to reduce the amount of thinking required to produce a conclusion for each row. But examining the statement shows that if P is false, it doesn't matter what Q, R, or S are, effectively eliminating half the cases in the truth table, 8 rows, with one explanation. For the remaining 8 rows, we can apply the same logic to show that when not Q is false, which means Q is true, everything in the parentheses becomes true. That would be another 4 rows of the truth table, so we've already taken care of 12 rows of the truth table with just a few statements. We could continue in this manner and show all possible cases in a few more short sentences. Clearly, in this case, identifying the possible true-false values of the logical expression is much simpler than trying to include all of this information in a truth table. Because we are simply describing the true-false values of each side of the logical equivalence, we can note that there are some special cases for which this method is even simpler. It would be sufficient to show that if both sides of the logical equivalency are tautologies, or both sides of the logical equivalency are contradictions, then they must be equal. That is, the left side is always true regardless of the values of the variables, and the right side is always true regardless of the values of the variables, as in the logical equivalency T or P is equivalent to P or T. Then we've shown that statements are both tautologies and logically equivalent. We could do the same thing with contradictions. If the left side is always false regardless of the values of the variables, and the right side is always false regardless of the values of the variables, then both statements are always false, and thus they are logically equivalent in all cases. Of course, these are special cases, since most statements will not be tautologies or contradictions, but contingencies. Having described how to show logical equivalence by showing that the statements have identical true-false values, there are a few more things to take note of. In general, this method is simple to understand, but with extremely complicated examples with large numbers of variables to consider, it becomes less obvious how to tell which values of the variables will cause each side of the equation to be true or false. Also, it is usually helpful to begin by starting with the broadest and most obvious statement you can make about both the left side and the right statement. As in our first example, P implies Q, we should start by showing the values when P is false, because it is a simpler and more obvious case to consider than when P is true. You should also be wary of existential and universal quantifiers when using this method to show equivalence. While showing that the statements using quantification are equivalent is not too complicated in logic, it is much easier to make a mistake when making a generalization about quantification to group cases together. The method employed here is only one of several methods that could be used, or even combined, to show the statements are logically equivalent. You should use whichever method is most appropriate for the situation.